Hi everyone. In this video, we're going to perform an experimental test of Newton's second law. Isaac Newton was one of the, if not the most important figure in the history of science. His work, Mathematical Principles of Natural Philosophy, also known as the Principia, was absolutely revolutionary in that it, among other things, developed a single framework that connected all different types of motions, from the motions of objects and systems on the Earth to the motion of objects in the heavens, the motion of the planets and other celestial motions. A center point of this work was Newton's three laws of motion, which seemingly apply to all types of motion in the universe, or at least the motions that were known of at the time. This was long before measurements of quantum mechanical or relativistic systems could be made. So again, this is incredibly important in the history of science, so let's look at Newton's three laws of motion. And briefly, Newton's three laws are as follows. The first law is that objects in motion will tend to stay in motion, and objects at rest tend to stay at rest unless an outside force acts on them. If there are no external forces, or if all of the external forces acting on a system are balanced, that object will keep moving in exactly the same way, the same velocity, the same speed, in the same direction, unless there's some unbalanced external force acting on the object. The second law is that the rate of change of the momentum of a body is directly proportional to the net force acting on it, and the direction of that change in momentum takes place in the direction of the net force. Let's talk about this one in a little bit more detail. Momentum is generally denoted by a lowercase p and is defined as the mass of the object times its velocity. So this is a vector quantity. The direction of this momentum is the same as the direction of the velocity. And Newton's second law says that the net force acting on the object is equal to the change in the momentum over the change in time. Well, this momentum quantity is mass times velocity, and if we are assuming that we have a situation where the mass of the object isn't changing, the only way that this momentum will change under those conditions is if the velocity is changing. So I can rewrite this as the mass times the change in velocity over the change in time, and your change in velocity divided by your change in time, how your velocity is changing with respect to time, that is just what we call acceleration. So we can write this in the case where the mass is constant. We can say the net force is equal to the mass of the object times its acceleration. It takes a net force to change the velocity of the object, to cause that object to undergo some acceleration. The third law is for every action, force applied, there is an equal but opposite reaction force. So equal force applied in the opposite direction. So if I have two objects, let's call them object A and B. If A and B interact with each other through some force, they run into each other, or there's a gravitational force or electric forces between them, no matter what kind of force it is, if A and B are interacting and A is applying a force to B, B will apply an exactly opposite force to object A. That would be our action-reaction principle. And these other laws, we're going to talk about them in other testing physics videos, but what I want to just say now is that these laws seem to apply to all different types of forces. It doesn't matter whether we're talking about gravitational forces or spring forces, frictional forces, air resistance. No matter what kind of forces we have, Newton's laws seem to apply to all of them. But at least for the purposes of this video, we're going to try to look specifically at Newton's second law. Our claim is that the net force acting on the object is equal to the mass of that object times its acceleration. Okay. So again, the net force is the vector sum, because force has direction associated with it. If I have forces going in different directions, I have to add them up differently. The vector sum of all the external forces acting on an object in newtons. M is the object's mass, that's going to be in kilograms. And A is the acceleration of the object, the rate of change of velocity, and we measure that in meters per second squared. So how are we going to actually measure this? Well, this setup that I'm going to be using might look familiar. I've had this set up in a previous experiment where we were talking about work and energy. We have this half-Atwood machine. So I have a cart that I've attached a force sensor to. I've got a motion sensor set up to determine how this object is moving. And I'm going to attach a string to this object, have that string go over the pulley, and then attach some hanging mass, which is going to cause the cart to move down the track. Basically, what we're doing is I'm going to be applying some forces to this cart, and we're going to measure how that cart's motion changes. How is it accelerating? And we're going to use this to try to test Newton's second law. So let's talk briefly about just some of the equipment that I have. So over here, I have a motion sensor. So if I put the cart on the track and I start data collection, well, if I move down the track, I move to a larger position. If I move back along the track, I move to a smaller position. And this is also tracking what is the velocity of the object. Okay. I also have a force sensor attached to the top of this cart. Let me turn this back here. I've got a force sensor attached to this. And if I start pulling on that force sensor, you'll notice it's measuring how much force is being applied to this thing. So when I attach a string to here, the string is going to pull on this hook at the end of the force sensor, and we will be able to measure what is the tension in that string. Now, we do need to make sure that things are properly calibrated. So I've tried to set this track up as level as I can. So if I put a cart here, it shouldn't move. And just to also make sure that we're keeping the track as level as possible, if I give this a small push in either direction, it should do basically the same thing when I give that cart a small push in either direction. So this is a fairly low friction track. For now, we're going to call it a frictionless track. That's an assumption, but we'll come back to that one later. So I've leveled this track as accurately as I can. There's always going to be some levels of measurement error, uncertainty. This is probably not level to the, to the nearest atom, but we're trying to level it as much as we can. The other thing that we have to do is make sure that our force sensor is properly calibrated. This thing does tend to drift a little bit, but we can just make sure that this is properly zeroed when we're doing each of these runs. Again, there is always going to be a certain amount of measurement error, but hopefully this is fluctuating around a force of 0. So looks like we're getting pretty good with that. And again, we're going to be taking that cart, attaching a string to it. It's going to go over the end of the pulley on this side. So I'll leave the camera kind of aimed this way so you can see the pulley when I start adding some hanging masses to this thing. And what we're going to try to do is measure what is the acceleration of this cart, and we can get that from the rate of change of velocity. This is probably something I should write down here. One way that we can find this acceleration is that when we're starting to take some data, I'm going to be able to get a graph of how the velocity is changing with time. We said that acceleration is the rate of change of velocity with respect to time. So I can measure the acceleration when I get this velocity graph by taking the slope of that velocity graph. The slope of that velocity graph is how we're going to get the acceleration. And again, we're going to have our force sensor measurements to figure out how much tension was in that string as this thing was moving. So that's the equipment that we're going to be using. And again, if we take this particular system, looking at the motion of the cart, and see what Newton's second law would claim about this system. Well, if we look at the forces that are acting on it, well, when this cart is on this track, the force of gravity should be pulling down on it. There should be a normal force of the track itself pushing up on the cart. And those normal forces and gravity in this particular case, those should just be canceling each other out because it's not going to accelerate up or down. And I've got a tension force pulling to the right. So if we just look at the horizontal forces on our cart, then the only horizontal force in this case is the force of tension, and that should equal the mass of the cart times the acceleration of the cart. Again, this is our claim. And the way that we're going to put this claim to the test is by applying a bunch of different forces by having different hanging masses on the end of this track. We're going to be measuring what is the acceleration of the cart based on the motion sensor data. And we're going to be measuring the force of tension. And then taking this data all together and seeing how do we try to identify this particular mathematical pattern and put this claim to the test. So let's start with an initial run. So I'm going to just move a few things out of the way here. And let's start with just 50 grams for the hanging mass. So I'm going to start with a hanging mass of 0.05 kilograms. So we're going to take our string, put that around the end of the pulley, put our cart on the track. There is a wire attached to this cart. Hopefully that doesn't cause too much interference when we're actually taking some of our data. And let me make sure that the force sensor is nicely zeroed. I'll re-zero the force sensor again just to make sure. So again, I'm going to connect the cart to our hanging mass. Notice we are starting to measure some force now. And let's see what happens when I take some data for this first run. So 3, 2, 1. I think I started the sensor a little bit late, so let me try that one again, because I want to be able to get the full set of data. Let's try that again, and I'll wait till all the sensors actually starting before I let the thing go. So here we go. 3, 2, 1. Okay. So let's zoom in on our data. Okay. Again, we need to identify what is the acceleration of the cart and what is the force of tension that was pulling on that string. So if I highlight this section of data from our velocity graph, we can identify, let me just kind of set this up so we can look at a couple of points. In fact, let me just click on the whole thing. We can identify what was going on at the beginning of the motion, what was going on near the end of that motion before we started to hit the end of the track, and we're going to look at how our velocity was changing over this period and the forces that were applied over this period. So if I highlight this set of data and I apply a linear fit, okay. So for that first data point, it looks like our linear fit, for the velocity data, we have a slope of 0.456. Just do 3 significant figures because I don't entirely trust the last one. Again, in any measurement, there's always going to be certain amounts of both random and systematic error, and we're trying to identify those properties. So we've got our acceleration, and if I highlight the same section of data, I can use the statistics to identify, well, what was the average value of the force during that time. So our force was 0.464 newtons. 0.464 newtons. This would be meters per second squared. Might as well put all the units in. Again, there's always going to be a certain amount of measurement noise, but by taking this whole data set, we're looking at 66 different samples. So a lot of that random noise should be canceling out. Again, you might want to have a look at the scientific critical thinking video on random versus systematic errors. We're going to be kind of expanding on some of those ideas in this video. Okay, so we've got our first data point. Gonna bring this back and I'm gonna add 50 grams to this. So we've got another system. So we've got this attached to the cart. Let me make sure the cart is still, the force sensor is still zeroed. Looks like we drifted a little bit, so I'm gonna re-zero that. And now we are dealing with the 100 gram case. So 0.10 kilograms. And let's see what we get for this run. So starting sensor. Okay. So again, we can scale these graphs because, again, there was more force applied in this time, so you have to rescale those graphs. And let's say I look at this data, the slope of our velocity graph. In this case, our slope is 0.932. So our acceleration is 0.932 meters per second squared. Again, acceleration is how velocity is changing with time. Velocity is measured in meters per second, and I'm seeing how that changes with time. So it's how many meters per second is our velocity changing by per second. And we also need the force data, so I'm going to highlight the same section. And let's look at the force data. So the mean force looks like it's 0.882. Again, we can kind of go through these graphs and, just look at some of the raw data in case people are interested in that part, saying what velocities did we start at what certain times, what velocities did we end at. There are other ways that we can use to measure this acceleration. So again, just trying to give as much data as people are interested in, or maybe people aren't that interested, but we'll give it a try. All right, let's take another set of data. So I'm going to add on another 50 grams. So this is now 0.15 kilograms. Going to do the same thing. Is our force sensor still zeroed? Need to click on that to see whether the force sensor is zeroed. Yep, still looks pretty close to zero. Around the pulley, straighten that out, and let's take our next data run. So here we go. 3, 2, 1. We'll scale our graphs again. Same kind of thing. So we can, once again, we can look at the individual data points. Go through there and highlight whatever data, going from some initial state, probably somewhere over here, to some final state over here. We can grab that data. Or we can use the computer to quickly calculate this slope. So our acceleration in this case was 1.353 meters per second squared. And our force, if we highlight that section of data, our force is 1.256 newtons. Well, let's see if we can get a couple more data points. So I'm going to add another 50 grams onto this. So now we're going to be dealing with 200 grams, so 0.2 kilograms. So I've got 200 grams hanging on there. Attach the cart. Get rid of this, and here we go. 3, 2, 1. All right, we can scale that. And once again, we can look at this in terms of individual data points, going from where the motion started to where the motion ended. So you can see the raw data. And then let's actually look at the slopes involved. So the slope in this case is 1.723. Our force is 1.604 newtons. And let's get one more data point. Try to get at least 5 data points. I might even do another very low mass case just to make sure we're getting as wide of a range of data as we can. So we're not just mistaking one pattern for another by only looking at a narrow data span. Attach this. So this is now 250 grams attached to this, so 0.25 kilograms. And let's see what we get for this next data run. All right. Once again, we can auto scale. Once again, we can look at the raw data from right near where we started this motion till right when we get near the end of this motion. So we can extract some of those data points if people are so inclined. So let's highlight that velocity data, get the slope of the velocity data, that is 2.078 meters per second squared. And our force during the same time is 1.925, again, for the mean value of that force. Maybe I will do one more with a lower mass. So I've got a 20 gram mass over here as well. So we're going to add on a 20 gram mass case. Just a nice small mass. Let's make sure that the force sensor is zeroed. Go through all of our best practices again. It looks like it's about zero, but I'll just zero it anyway. Let's go with this one. So 3, 2, 1. Okay, need to auto scale these so we can see them a bit better. So it took a while longer. Get some different looking data here. So we want well, let's first look at the raw data. Okay, so you can find at some early times, some low velocities. As time goes on, those velocities get higher. So we can extract some of those values if we want. Or again, we can use the computer to calculate what is the slope of this graph. Maybe I'll see if I can fit this on here. So 0.02 kilograms. That acceleration is 0.159 meters per second squared. And let's look at the force value for that same region. So that is 0.181. Okay, I think we have some good data to be going on with. Now what we want to be able to do is say, how can we take our data and look at any patterns that are formed by that data to identify whether or not this data supports or refutes this particular claim from Newton's second law. So let's set up a new kind of table. So I've set up a new graph where I can input these accelerations that we've measured, these tensions that we've measured, and see if we can generate a graph for measured acceleration on the horizontal axis and measured tension on the vertical axis. So let me just add these in. So our accelerations were 0.159, 0.456, 0.932, 1.353, 1.723, and 2.078. So those are our accelerations. And now we want to enter in the tension. So that was 0.181, 0.464, 0.882, 1.256, 1.604, 1.925. Okay. And then definitely have to fit this graph. Notice when I take those data points and put them all together, we get this very, very nice straight line. In fact, let me see if I can make those data points show up a little bit better. Okay, that works a little bit better for seeing each of the individual data points that we found. Whenever we gather data, we want to try to find patterns in that data. And if we talk about our different kinds of patterns that we've discussed, the linear fit, quadratic, power fits, exponential fits, this one looks very, very linear. So I'm going to apply a linear fit to this data. And we notice that that linear fit very, very accurately goes through basically all of our data points. There seems to be very little random noise present. In fact, I can change this and also show the uncertainty levels on this table. So let's see what we can do with this. Our data, when we did this graph with the measured tension on the vertical axis, so let me draw this one out. So we've got measured tension on the vertical axis and acceleration on the horizontal axis. We got a bunch of these data points, we got this line of best fit, and from our data, we get this best fit equation where y, the thing on the vertical axis, is equal to 0.905 times x, the thing on our horizontal axis, plus, this looks like 0.041. Okay. This is what pattern our particular set of data that we've just gathered makes. Our claim was that the force of tension should equal the mass of the cart times the acceleration. Okay. And what we want to do when we have a claim and some data and we want to compare how those match up with each other, we want to take each of these terms and try to line them up with each other to see how we can give physical significance to these best fit parameters that the computer kind of spit out at us. Well, on the vertical axis, on the y-axis, we put the tension. So those quantities match up with each other. The thing we put on the horizontal axis, well, that was our acceleration. The acceleration and what we have on the horizontal axis, those should match up with each other. If we continue lining these up, we should have that this 0.905 should match with the mass of the cart. If Newton's second law is correct, we should get a linear fit for this data, which it looks like we have. And that 0.905, that thing that we got from the slope of this set of data, that should match up with the mass of the cart. Well, let's test that out. So I've got a scale over here. And again, our claim is if I take this cart and I measure its mass should be 0.905 kilograms or 905 grams. If Newton's second law is correct and if we've done this experiment correctly. So when we put this on here, I get 897.7 grams. So our true value of this mass, so the true mass was 0.898 basically kilograms. And the mass from our experiment was 0.905. Those are in pretty good agreement with each other. Okay. It is very unlikely that those two numbers would match that accurately purely by chance. That would be very, very unlikely for those numbers to happen purely by chance if we didn't have at least something going correct with this model for Newton's second law and for this specific cart system. Notice that this slope also has some uncertainty. This has almost 5 grams of uncertainty, so this is just outside of one standard deviation. We haven't really talked about standard deviations before, but it's a measure of how much random uncertainty does there seem to be in this, how reliable do we think that this 0.905 is, and it's just outside of one standard deviation, which is pretty good agreement. If we were to do a percent difference calculation by taking the magnitude of the difference in those two values divided by the true value, we'll take the mass that I got from the scale, that's going to be probably the more reliable one, and then multiply by 100%. If we take that difference, so 0.905 minus 0.898, take that and divide by 0.898, and multiply by 100, it's less than 1% off. It's about 0.8% off. That's pretty good accuracy. Okay. But maybe you're saying to yourself, why did we have to take multiple data points? Why did we take all of that data instead of just taking one data point saying, this is our acceleration, this is our force of tension? If I take a single data point, I should be able to use that to get the mass of the cart. Well, let's give that a try. Let's say I take the first data point that I actually took, the 50 gram case. So we have an acceleration of 0.456 meters per second squared and a tension equal to 0.464 newtons. Okay. If I just rearrange this and say my mass should be the force of tension divided by the acceleration. In this case, if I run through those numbers, 0.464 divided by 0.456, I get 1.02 kilograms. It's not terribly far off from the 0.898 that we got from the scale, but it's around like 10% off. Much worse than the 0.8% off. Maybe that was just a bad data point. Let's take the 150 gram case. So our acceleration in that case was 1.353 meters per second squared, and our force of tension was 1.256 newtons. Okay, so we do that force of tension, 1.256 newtons divided by 1.353. Still, I get a mass that's too high, 0.928 kilograms. It's still too high. And if you go through all of these, in all of these cases, you can try the numbers for yourselves, you'll get significant overestimates on what the mass of the cart is. So if we look at our errors in this case, there seem to be a pattern in the errors in how we've actually done this experiment. And if there's patterns to the errors, there's some sort of systematic error happening. There's some sort of systematic effect that is changing the results of the setup that you have. If we go back to here, this comparison of our claim with our data, when we got this best fit equation, our y-intercept was 0.041. What would we have expected it to be if our claim was perfectly true and we've done everything perfectly? Well, if we're comparing that, it should be 0. There shouldn't be anything there. And notice that our standard deviation is significantly smaller than the value for our y-intercept. So we're multiple standard deviations out. This is not likely to actually be equal to 0. So even though we got the mass matching up very accurately, there seems to be some kind of systematic error. So what might be causing it? Well, we said at the beginning, we're going to assume that this track is frictionless. And that's not going to be a great assumption to make. This track is low friction, but it is definitely not no friction. So let's see if we can actually improve on our model to see if we can get this data to fit a little bit better. So instead of having a frictionless track, we are now going to just say this is a low friction track, and we now have this additional force acting against the force of tension. Friction is trying to act against the direction that the object will move in. So in this case, when we write out Newton's second law, instead of it just being the force of tension equals the mass of the cart times acceleration, we get the force of tension minus the force of friction equals the mass of the cart times the acceleration. And if I do a quick rearrangement of that, we get the force of tension equals mass of the cart times acceleration plus this force of friction. So in our claim, if we have this better model where we're now saying there's going to be some friction on this track and we want to be able to account for that, we add on this force of friction. And now with this improved model, we can say that that 0.041 Newton value, that's actually a measure of the force of friction that's acting on this system. This model of saying the friction that we're going to have for this cart on this surface is just going to be the same force of friction the entire time, that matches up with our data. We found a systematic error where the kind of naive methods of measuring the mass from just single accelerations and single forces, that kind of gave us consistent answers that were consistently off from the expected value. And that source of systematic error allows us to identify and improve something that was missing in our model, the fact that there's friction acting on this system. So identifying these patterns in data and identifying when a source of systematic error will be present, we can identify that sometimes from our data and we can account for it. Notice in this case, the fact that we introduced some friction doesn't actually affect anything about how we measure the mass of the cart. We still get that when we generate this tension versus acceleration graph, the mass of the cart stays the same. We could have a huge amount of friction on this track, and we'd still be able to use this exact same method to get to a reasonably high accuracy the mass of the cart. In a lot of intro physics labs, whenever students are asked what are some sources of error, friction is always going to be the scapegoat. In a lot of experiments, students will just say, oh, there's friction acting on this system and we didn't take that into account. Well, in this case, as far as measuring the mass of the cart is concerned from this data, the friction doesn't actually affect that. So we've gathered some data, we've built an original model, and then later improved that model to figure out how does Newton's second law apply to this particular system. And we had a way of actually testing the accuracy of Newton's second law, and we got very, very good matching between the true mass of the cart that we get from our scale and the mass that we got from looking at this pattern in the tension and the acceleration data. Again, these methods of finding patterns in data and using those patterns to identify what these fit parameters match up with, this is used all the time. So again, this is strong evidence in support of Newton's second law, and in future videos we'll basically be looking at other cases where Newton's law comes into play, and we're going to, again, see more and more cases where Newton's second law does actually reliably match with the data that we're taking. Now, one last thing that I want to quickly mention about this is if you're doing this experiment on your own, you don't actually need a motion sensor or a force sensor to do this experiment, because we can actually do this experiment a little bit differently. So this is just in case someone is interested in trying this experiment for themselves, but again, having access to motion sensors and force sensors, it's a little bit limited, but let's play around with it like this. Let's say I've got a track and a pulley, and we've got this cart and hanging mass system. So we've got, if I look at the external forces acting on this entire system, the cart and the hanging mass together, and the things that are going to propel that system along the direction of motion, so the cart along the track, and then the hanging mass downwards, we can kind of write out our information a little bit differently. We can say, I've got different hanging masses, and I've got this cart. There's going to be a force of gravity pulling down on this hanging mass, and presumably there's still going to be some friction acting against the cart. If you want to do this experiment on your own, this would be the setup that I would recommend. You've got a cart, you need a cart, a pulley, some hanging masses, and some sort of level track in order to do this. When you're going through different trials, instead of just adding different masses, move masses between the cart and the hanging mass so that the total mass of the entire system stays constant. So for this hanging mass, maybe you have a little plastic bag and you can put masses in there. And when you want to reduce the masses, take those masses out and put them into the cart. So the total mass stays the same throughout the entire experiment. Then the force of gravity, this force that we're measuring, instead of using a force sensor, we can just say the force of gravity pulling on this hanging mass is whatever the value of that hanging mass is. So you need some kind of a scale so you can measure how much mass is attached to that, times little g, which is 9.8 meters per second squared. So measuring the force, you've got your hanging mass times 9.8 meters per second squared. And if your hanging mass is in kilograms, so this has to be in kilograms, then that force that you get will be in the units of newtons that we need for this experiment to work. You can also calculate the acceleration by looking at how much time it takes that mass to fall a certain distance. So I'm not going to go through the full derivation of this, but from kinematics, if I am releasing this system and that hanging mass is falling downwards, starting from rest, so we start the timer when we first let go of the system and time how long it takes to reach the floor or something like that. If it's traveling a distance d in a time t starting from rest, the acceleration is just equal to 2 times that fall distance divided by the time squared. So this distance would be in meters, and this time would be in seconds. When you're timing things by hand, I recommend using masses and using a setup where the times that you're measuring are at least 2 or 3 seconds. Timing something shorter than that with a stopwatch, not going to be super reliable. But using this equation, you can actually get the acceleration in meters per second squared. A distance divided by a time squared. And then your equation, if you're focusing on the external forces, which again is what Newton's law is talking about, and we're considering this entire system, we can write this as the force of gravity pulling down on this system minus the force of friction is equal to the total mass times the acceleration. And then if I just move that force of friction to the other side, I get the force of gravity on the hanging mass is equal to the total mass times acceleration plus that force of friction. So with, again, not too much equipment, you can actually try this one for yourselves. If you do try it and want to talk about your results in the discussion, in the comments below, that would be fantastic. I'd be really happy to hear if people are trying this for themselves. Again, don't believe me. Look at the data. Does the data support or refute whatever claim is being made? So that's going to be it for this video. Again, we're going to be looking at other cases of Newton's second law in future videos as well. As always, thank you for the view, and have a good rest of your day.